Okay, I'll continue on with working on the little amplifier here. Where I left off last time was I had the tube, the grounds wired, and what I've done is I've mounted the tube on the plate. I've added the plate choke, a parasitic suppressor. I'll point out on the schematic what that is. This actually keeps the tube from going into what's called VHF oscillations and keeps the signal a little cleaner. This is a cap to ground. The high voltage, the 700 volts, is going to tie in right here. With there's one piece that's not hooked up yet, and it's because the coil, we've got to figure that out, and I'm showing you this setup here on how to figure out if your turns and your coil's right. I've wired up the relay. That's this part right here. I've made this connection over. Actually, it's probably better if I use this schematic. You can see what's going on. There's a capacitor in line here. There's a little 22 microhenry choke. This is kind of a trick little thing in there. What this does, when the relay is switched to the tube, the cathode is grounded so that the negative can flow through that coil and into the cathode of the tube. And when the relay is in the receive position, well, this is drawn wrong, by the way, so make note of that. I put this in here by mistake. Anyhow, there wouldn't be any connection going to the cathode during receive, so that effectively shuts the tube off. Then transmit, that connects and ties this in. This cap is more or less just a DC block in case there was something in the radio or whatever. It protects the radio if something should happen over here. This cap is a 10 picofarad sampler. That's this little cap right here that I've got tied in. This cap going to the connector is the 0.01. And this is a 10 picofarad sample cap that'll sense the RF coming in to trigger the RF transistor to key the relay. And I'll show you that little device. We got a couple diodes. They're in the form of a voltage doubler. And they charge a cap and with a positive voltage. And we use a 1K resistor tied into the base of a transistor. And this is kind of a timing circuit. If you was to use sideband, instead of going larger on the cap, you could just simply switch a larger resistor up to maybe 4.7K if you wanted a time delay. What it is, there's current drawn through the transistor and it discharges the cap. So all it takes is a little bit of current or voltage to key the transistor. So we use a resistor to keep the cap from just dumping everything it can through the transistor. So a larger resistor would make the transistor stay keyed longer. This resistor here is a kickback, anti-kickback spike suppressor. A lot of times I don't use these, they're not needed, but if you had a sensitive transistor with maybe a low collector voltage, say it couldn't hold off any more than 30 or 40 volts, you might want to put a diode in there. When this is switched off, there's a field that when it collapses can create a back EMF, and sometimes is the reason for damage in the key-in transistor. Sometimes you'll see these drawn on commercial amps. Sometimes they'll include it in the relay. Other times they just omit it, and you can assume it's there, or you can add it if you want. All it is a 1N 4001 like a power supply, small power supply, 2.5 amp rectifier. Okay, so on this lead here, the relay going down to the cathode, that's this wire, going to the cathode. Get another pointer here, I might get my hands out of the way. We have the antenna side. That's this link here. This little loop simply lets the radio go through the relay without doing anything and going to the antenna in standby. And that is this little wire right here. Now, this line I don't have tied in yet. That'll be this terminal right here, and that would be, when we're all done, that'll be a piece of coax that goes from here up to the loading capacitor. Now, just to save time, I went ahead and wound this and checked it out, because this is kind of a boring procedure to watch this, but all it is, I have taken some 16 gauge wire. For just what I had on hand was a AA battery, and I just wound it around the battery as a form. You could use like a 3/4 inch wood dowel, use that for a form. This little capacitor is what I call a padder capacitor. If I had a larger or more capacitance in this load capacitor, I wouldn't have to use this. I'm using 110 here because this loading cap is only like I think it's a 200 puff, and most of the time you'll need a 360 or a 400 puff variable cap. But I just didn't have one that mounted with a threaded collar, so this was more convenient. I just had to use a little padder. Alright, to figure out your coil, you look in the tube chart to find the plate or load resistance of the tube. Once you find that, you find a non-inductive resistor, and here what I have made up, this ends up with an ohm meter. It measures 9,000 ohms. The tube data sheet lists the tube at 9,900 ohms. So if I'd have had a 10K 5-watt resistor, I would have put that in there. But these are 2-watt carbon, they're non-inductive, so I've just paralleled them up until I came up with 9,000 ohms, 9K. The number of turns on here is 14 turns that I've ended up with. 14 turns on a 1/2 inch diameter. That's a AA battery. If you was using a larger diameter like a 3/4 inch, you might not have to have but maybe 12 or about 12 turns probably. As you add more tubes, the resistance is going to go down. So if I had a pair of these tubes in here, I would aim for having maybe a 5,000 ohm resistor here. Because you add tubes, you parallel them, it actually cuts the resistance in half for each tube. So if I had 2 tubes, the load resistance would be 5,000. This resistor is only in here for right now while we're trying to get the coil tuned. This saves you from having to actually activate the tube with high voltage and take a risk of getting a shock while you're adjusting or making different turns. And all I'm doing, I've got an SWR meter. The radio side of the SWR meter is hooked to a CB radio. The antenna comes around here and it's tied in to my load cap. So I'm actually, it's kind of like feeding power backwards, but a Pi network, the RF will go either direction. It doesn't care as long as the load on each side matches what it expects to see. So the radio wants to see 50 ohms. So we want, when we're done, the output of this is going to be a 50 ohm match to an antenna. So we feed power back through it. We represent the tube by a 9,000 ohm load. So if we key up here, I'll throw one of these off just to show you. Alright, so I've adjusted the meter calibrate it for forward, full forward. Now you put it in reflected, and we got a high SWR. So you just vary your caps until you get that as low as possible. And this is the easiest way I know of safely finding the right amount of turns. Now, like if I couldn't get that low enough, if I still, no matter what I did with the caps, and as long as they have range, in other words, you wouldn't want your cap wide open that way or fully closed, that tells you that you're off too far one way or another. Or if it's all the way closed, it would tell you that you don't have enough capacitance. But this circuit is tuned pretty good. It's just a little past mid-range, which is good enough. That would get you by. Now, if you had a situation where you couldn't, like if you balance these out and you still had some SWR, what you might start doing is take a soldering iron and you can bridge one turn to the next and then retry everything and see if that lowers your SWR. If you end up with a higher, in other words, if it climbs a little bit and you can't get it back to where you were, that tells you that you don't have enough turns. So you'd just take the coil out, remake it, adding at least one more turn. Me, if this was just a test coil, I would make 3 or 4 more turns, and then once I found the right number by shorting out the turns, then I would take it out, remake a coil with just those number of turns being used. Okay, now from here we need to find out, basically it's not important, but if you wanted to start making a chart to track where you've gone with one tube to maybe add in another tube, and you wanted kind of something to go back and look at when you maybe you wanted to build another one, very carefully, let me get these, okay, low as I can get it there. Now, okay, what I would do, you get the soldering iron out and you start unhooking these caps. You want the load resistor off. You want it out of the way. We want to take the coil off. And then we want to take the coax off. Well, it's going to fight me. Okay, we'll do it the easy way. Okay. Now, the patter cap will leave on. We'll just leave it in place because we want to know what the total capacitance of that is. So now, yeah, now I've lost my cap meter. All right. Okay. Now we can put this in here. Hook that one to ground. Okay. Hopefully the meter, you can see that. Yeah, all right. That's 32, basically 32 picofarad. That's what our cap is resting at when everything was in resonance. 32 picofarad. Now we can do the same thing. Just move this over to the other cap. I'll leave this one grounded. Okay, it's more than 200 puff. It comes out that when this one's in resonance, we're at basically 208, right at, we could call it 210. There it rested at 2.7. So that's 207 picofarad for the output cap. So you can see with this 110 patter, this capacitor wouldn't be enough right at that point. It would be almost closed at that. So that's why, like I say, if I was to redo this and put it in a cabinet, I would look for maybe one of the ones they call a broadcast band variable, which's got a lot more fins, and usually they're at 365 or 400 puff. But this would get you by using a patter. The criteria on this little disc for this one tube, this would be okay. It's only a 1 kilovolt cap, 110 picofarad. You could get by with using a small cap like that. If you had, say, over 100 or 200 watts, you would want to then, see, do I even have it here? Okay, you would want to start using a patter capacitor that look like this. I don't know if the camera can pick that up. This is called a doorknob. And this one here is 100 picofarad. It has a threaded end on each end that you can mount with a screw. So you just drill a hole, you'd run a screw through your chassis, then you'd put a solder lug on this end and run a little stiff piece of wire over, and so it would be sitting in there like that with just a little piece of wire running over. Now this will handle up to and above a kilowatt, and these are like, I think they're rated, most of them are rated at 3,500 volts. But as your power goes up, this would have to change to something that would handle more power. But for this little rig, we're going to get maybe 50. We might get 75 watts when we're all done. And okay, oh, we can hook up the little keying circuit. We can get that done this time. Let's move that out of the way for now. Okay, on here again, there's the keying circuit. Hopefully that's, let me get it in the camera. These are 1N 41/48. If you had 1N 914s, you could use them. The capacitor I got here was only 100 microfarad at 25 volt, and it wouldn't have been enough, so I just put them in series. Caps add in series, or actually add voltage. The 25 volt, if you add it in series, you're going to have 50 volts hold off, but the capacitance goes the other direction. So the two in series would give you 50 microfarad, and the cap ends up 50 microfarad at 50 volt. A little more than what it shows here, but for our little circuit, and there's a little 1K resistor right there. If it keyed up too long, I could always shorten that down to maybe 470 ohms or something. But that ends up going right here. This is where get around there. Upside down. There we go. Okay, I've just soldered that to that ground on the copper, and that'll hold it in place. Now we come with the gonna have to move it a little closer. lead won't quite reach the relay, so I'm just going to move that over to where it will. Okay, that part's in. Now, let me trim these diodes here. That little 10 picofarad cap, the sample cap, just simply goes right there. Get it where that will relax. Put some solder. Okay, now our input circuit is completely done. That's ready. Got to solder the wire that goes to the one side of the relay. This goes to the coil. We're soldering this collector over to the coil. Okay, so that just about does it for this section. What I will do is I will hook this up, and I have a cap I've got to find that goes from the top of the RF choke over to the load or the tune cap, and I think it's this one. Now this is another one that's going to have to be high voltage. This is a 0.01 at, I think it's 3,000 volts. And that capacitor is this one right here. There's the plate choke. The cap at the bottom of the plate choke I've showed you, that's this little orange drop. There's the plate choke, and then this cap right here goes to the tune. And that'll go from there to there. And then we'll hook this up. I got to find my power supply, get it out, and so on the next video we'll hook up a filament lead here at 6 volts, a ground, and 700 volts, and we'll fire this thing up. Oh, and 25 volts will have to go to the other side of the relay to activate when we have RF current to there. On here, if you can see these little connectors, yes, they don't look like an SO239, and because they're not. I have a lot of what's called Bnc cables. They're just a push quarter turn, they lock on, and it's just easy for me to use these because you drill a hole, feed them through, put a ring nut and a lock washer on it, and you're done. The larger ones have to mount with screws and got to punch a great big hole. For me, just changing around with this, since I'm experimenting, I just threw these in there. It's just easy, and then I have adapters that plug on from here and go to it changes this to a PL259 to go to my meter and my radio. So that's why these connectors look a little different, but they'll work. If you find them, you'll see that they're just easier to use if you get the cabling to go with them. Okay, as always, any questions, or if you'd like schematics, get that in frame. Drop me a line if you want. If you want schematics for any of my projects, we keep on going here, so you can have the schematic to work with, so you can see where we're at when we're putting parts on. Drop me a line and I'll shoot you the email back with the schematics. They're JPEG format. They are small. Most of them are around, from 56 to maybe 80, 90K, 100 and some K. So they're easy to send through the email that way. And like I said, they're all JPEGs. Alright, thank you for watching, and we'll see you on the next video, and we'll see how much power this little tube will put out.